Hi, my name is Sankalp Yadava, and my project is a statistical analysis to measure trends in water depth in agricultural wells across California. I'm a third-year student at the University of Virginia, majoring in applied statistics, and I was kind of hoping that my findings would have real-world implications as it relates to policymaking and economic decisions. During my 8 weeks at Agate, I supported my mentor Mandy Wilson with data and statistical analysis on a number of different data sets, including the validity of ag-similar data sets in Washington State, a deep analysis of open data sources for the state of California, and her preparation for creating a California ag similar data set, and also the analysis of their livestock digital twin for the entirety of the United States. For the purposes of this presentation, I focus my analysis on the groundwater in the state of California and different statistical methods to measure the trends from 1980 to 2024. The California has seen a lot of decreases in the amount of water due to a number of droughts and numerous wildfires. This project examines groundwater trends in California through analysis of water depth associated with agricultural wells to see their specific impact on this trend. Different statistical tools like Mann-Kendall test and linear regression, which I will explain later, I evaluated these changes in water levels to identify statistically significant trends across the counties in California. This resulting model and analysis will be used to make strategic recommendations about water use, crop management, and economic impacts. My problem that I went into this project with looking at through the lens is how could we identify areas experiencing groundwater declines in the state of California to further our understanding of where supportive interventions may be necessary. In order to do this, I looked at two main data sets. I looked at the IOA groundwater level changes, which included all the information on the wells in California, and the Land IQ parcel data set that has all the agricultural parcels in the state of California. The problems that we faced with the well data is that there was no accurate amount of volume that was in each well, but they gave us the well depth and they gave us the GSE GWE, which is the height between the top of the well and the top of where the water was. And what I did is I took the well depth and I subtracted it by the GSE GW to get an estimated water depth. However, this is not an accurate estimate of how much volume is in the water, but it is adequate enough to graph the trends and changes of water level. In order to identify which wells were agricultural, we took our well data set and we filtered it by water use. And we found that irrigation, industrial, and stock watering were the wells that were closest with the land IQ parcels that were within 5 kilometers of them. And as you can see, there are 7,020 wells that were matched with 6,246 land IQ parcels within that 5 kilometer parameter. And there were only 27 wells unmatched. And the only problem with this data set is that the land IQ parcels don't show the livestock, which could have even improved the irrigation, industrial, and stock watering filtering, as the stock watering part of the data set isn't as affected. As you can see on this first graph, you can see all the matched wells with the land IQ parcels. And if you could look closely, there are still some blue, but the matched wells are so close to the land IQ parcels, we can assume that they are directly related with these parcels. And then in the next data set, you can see all of the matched land IQ parcels from the graph before, but now you can see different red dots, which is all the unmatched wells, which aren't near any of these land IQ parcels, which is the 27 from the last slide. So to see the trends, we looked at the data set from 1980 to 2024, and I compared the agricultural wells to all the wells, and I looked at the averages for these, and I took the averages per water depth per well year, and then I took the county average across all the wells per county. As you can see in the top graph, that is all the averages for the agricultural wells, and the bottom is all the wells. As you can see, there are examples is like in Fresno, it is around 500 in 1983, and then the next year it goes way higher. I chose the Mann-Kendall and the linear regression test to test the magnitude of these trends because the Mann-Kendall is a non-parametric method that doesn't require the data to have normal distribution, which benefits highly skewed and non-normal data, kind of like this data set where there's a lot of missing different data sets. And it's also a rank-based method with extreme outliers not having a heavy influence on the data. And this method has been proven to be very beneficial for agricultural analysis. And then I also chose linear regression because it provides a clear rate of change in R squared value, signifying how strong that rate of change is. And it is very strong at detecting linear trends. And these are kind of the different variables I looked at with the Mann-Kendall test, highlighting the sense slope to detect the trends, and then the increasing, decreasing, no trend. And then for the linear regression, the annual rate of change and the p-value signifying how important it is in the R squared. And so you can see in these tests from 1980 to 2024, And I chose 1980 specifically because when you look further back, this data set actually goes back to 1920, but there's a lot of missing holes for different counties, counties not fully reporting, and not enough data for it to be statistically significant from 1920. But when you look at it from 1980 to 2024, when you look at the agricultural wells, there's a lot of blue indicating that there's actually an increase in the well water depths, which is not consistent with our hypothesis that the agricultural wells would have a decrease in water levels. But when you look at the overall wells, not just agriculture, you can see a lot more red. You can see a lot more statistical significance. And this one, there's a lot more gray indicating insignificance in the tests. And then when you look at the linear regression, you see similar trends where for the agricultural wells, there's a lot more blue, and in the all the wells, there's a lot more red, showing that the agricultural wells, maybe there's not enough data, maybe the counties are misreporting, there's not enough statistical significance, there's not enough data to prove that the agricultural wells are the ones that are affecting this overall decrease in water depths. And some of the shortcomings that I faced when I was looking at this data set was I already mentioned the counties under the agricultural wells weren't statistically significant enough, as a lot of the counties were lacking data for their wells. Also, in the well data set, there were over 30,000 wells that were unknown, where there was no idea where the water use was. And these wells could have been agricultural wells, which would have been beneficial for these counties, and they would have had higher significance in their data just because there would have been more data behind it. And there are also just other factors that influence these trends, just like surface water availability, precipitation, water deliveries, or seasonal and geographical factors. And some of the future analysis I'm planning on doing with this data is I'm going to compare these trends with the annual precipitation and see how rainfall is correlated with the levels of water in agricultural wells, and if there's any strong correlation between those. And also just a comparison with the points of diversion to see how much water is being used and allocated from these agricultural wells. I just want to thank everyone. I want to thank Mandy and Samarth for being great mentors in this project. And yeah, I had a great time. Thank you.